Hello, everybody. Good morning and good afternoon. My name is Alexandra, and I will be your webinar host, which means I will be handling all of your questions and answers. During this presentation, I have enabled the questions panel, which you should see at the bottom right-hand corner of your screen. You may need to push the plus sign to expand the panel. This session is being recorded and will be made available to all attendees should you care to listen to it again or share it with colleagues. Now, I would like to introduce our speaker for today, VP of Product Management, Scott Register, who will present the 4 keys to understanding TLS 1.3 and active SSL. Scott, go ahead and take it away.
Thank you, Alexandra, and thank you everyone for joining us today. The internet, this great, wonderful place that we use for social media and online shopping and talking to friends and doing business and talking to our business partners and doing all that stuff, is this great, awesome, wonderful place, and we think it's just magical and wonderful and filled with unicorns and pixie dust. But there is a problem with a lot of the underlying kind of tenets of the security or the security of the internet, and that problem is Eve. And we'll talk all about Eve shortly. So what we're going to go over today, 4 big keys to understanding the new encryption standard that's coming up, TLS 1.3. We're going to go over a brief introduction to public key cryptography and how it works, and then talk about the benefits and some of the challenges of static key encryption, which is what we're largely using today, and then talk about some of the practical implications. There's this new encryption standard coming out, TLS 1.3, what it means for deployments in your network, and how Ixia can help you work through some of these things. Now, I will warn everyone, there is math ahead, so don't get tripped up. But I think it's going to be important, if you haven't seen sort of how public key crypto works, to see and be exposed to some of the basics here, so that when you see some of these terms, they will make sense, and you'll understand why we're changing some of the things that we're changing. Okay, so introduction to public key crypto. A key, when we say a public key or a private key, it's really a pair of numbers. There's a number for exponentiation and a number for a modulus. When 2 entities communicate using encryption, each one, when you're using this kind of encryption scheme, has a public key and a private key. Now, typically, the public key is used to encrypt data, and the private key is used to decrypt it. And those numbers, by the way, are very large, and they are different. Now, public keys, as the name implies, are available to the world. They're freely distributed. Everyone has access to them. But private keys are kept secret. And that's why I say that the public key is typically used for encryption. So this means sort of anyone out in the world can encrypt a message for you using your public key, and then only you can read it using your private key. So in this example, we're going to talk about 2 people who want to establish a secure communication, Alice and Bob. And here's how Alice's public key is generated. It's going to work the same for Bob, but we'll sort of ignore poor Bob for now. Now, in reality, Alice and Bob would each select 2 very large prime numbers. But just to make it readable, in this example, we're going to pick small numbers. We're going to pick 5 and 11 as our prime numbers. Now, Alice is going to multiply those 2 numbers together, and this produces the modulus. Okay, remember I said you've got a modulus and an exponent, so this is how we get the modulus. You just multiply them together. She picked 5 and 11 as her primes. I multiply those 2 together, and so my modulus now is 55. Now, I run a quick mathematical function where I just select 1 from each of the 2 numbers that I picked. I multiply it together, and I get 40 for the public key. This will be important later. Now, Alice selects a number that is relatively prime to and smaller than 40. So in this case, Alice will pick 7. So relatively prime just means it can't be divided evenly into 40. Okay, now Bob would go through the same thing, but for SSL, and by the way, for purposes of this discussion, SSL, which is Secure Sockets Layer, and TLS, Transport Layer Security, I and most other people use those interchangeably. SSL was actually the kind of first set of standards that was superseded by TLS, but typically people use those interchangeably. And in SSL, really only the server matters. The server is the one with the well-known, public key, and so Alice in this example is going to be the server. So we really only care about her. So her public key pair is 7 and 55. Exponent 7 modulus is 55. Okay, now let's look at how we calculate Alice's private key. A little more math here. Okay, so to get her decryption exponent, I take 1 over the public encryption exponent to the negative 1, or I'm sorry, 1 over the public encryption exponent, and then I take you take the modulus of her public key. So if you copy the information from the previous slide where her public encryption exponent is 7, I get the public, and I just multiply both sides of the equation by the public encryption exponent, get the private exponent times the public exponent, mod 40 is equal to 1. I solve for that, and I see the solution is 23 for private decryption exponent, because 23 times 7 is 161. 161 mod 40 equals 1. Okay? Hopefully that makes sense. Oh, by the way, if someone hasn't had high school math in a while, as I know I haven't, if you don't remember modulus arithmetic, modulus just means if you divide one number into another, the modulus is the remainder. So when I divide 40 into 161, it goes 4 times, and the remainder is 1. Okay, so now her private key, which again it's a pair of numbers, exponent and modulus is 23 and 55. Now, something important to note here, the public and private key are symmetric. That means I've got different numbers at either end. The private key is not the same as the public key. The private and public are different, as opposed to symmetric key, which we'll talk about a little bit later. So here's an example where Bob wants to send a message, in this case, the number 2 to Alice. So remember, we encrypt with a public key, and we decrypt with a private key. So her public key encryption exponent is 7, her private key exponent is 23, and the modulus was 55. So for Bob to encrypt his message, he takes that plain text, which is the number 2, he raises it to the public encryption exponent, which is 7, and then he takes the modulus of that by 55. So that's 2 to the 7th mod 55, that's 128 mod 55. So if you divide 55 into 128, you get 110 with a remainder of 18. So that is the encrypted message that he sends to Alice. Okay, now, and this to me is really where the magic is. Decryption of that message is really simple, and it's basically the inverse. So to do the decryption, I take that encrypted message, the ciphertext, I raise it to the private decryption exponent, and then I take the same modulus. So that's 18 to the 23rd power, mod 55, and you'll have to trust me on the math on this one. So 18 to the 23rd, mod 55 is that big number, mod 55. Basically, you divide 55 into that number, and you get a remainder of 2. So boom, Bob's your uncle, or at least Bob's your communication partner. Bob has successfully encrypted a message, sent it to Alice. Alice was able to decrypt it. All right, so that is a quick example of how public key cryptography works, which means there's a public key, there's a private key. You use one key to encrypt, the other key to decrypt. And even if someone is watching that exchange, they can't read the number 2, right? Because they don't have those keys, and so they can't. Even though the two communicating entities, Bob and Alice, may be talking over an open, insecure channel. Someone who's just observing that exchange can't figure out what they're doing, can't read that number 2. So that's a pretty big deal. However, there's a lot of math involved in that. There's a lot of computation that's involved in every message if you're doing all that work. So in practice, what we do with that public-private key setup is we really just use that to establish what's called a session key. And a session key is symmetric, which means we use the same number at either end. So we go through the exchange that we just went through, and basically you could use 2 in that example as your symmetric key, and so we'll use the number 2 to encrypt and decrypt. We'll use that as the key to encrypt actual data in transit. Okay, so that key exchange that we went through is really used in practice to establish this symmetric session key, because that's again encrypted with Alice's public key and then decrypted with her private. Okay, and again, Alice's public key, well known, advertised to the world. Bob can encrypt something with that, send to her, and she can decrypt it. Okay? Now, back to Eve. Remember the first slide, we talked about Eve. So here's the problem that Eve sort of poses to the internet. So as we discussed, when Alice and Bob communicate, their actual traffic, the actual payload, the context of their email, their communication, is encrypted with a symmetric session key. That session key, again, is secured with Alice's public key and can be read with her private key. Well, what happens if Eve happens to get a copy of Alice's private key? Well, she can decrypt any communications they have because they're using static keys, right? That the math that we went through would be the same anytime Alice and Bob talk. And in fact, anybody who's talking to Alice, a whole exchange, figure out what the key is, and then could read that Bob and Alice, or Frank and Alice, and anyone else and Alice happen to talk about, because she can decrypt it. She doesn't have to interfere with the communication. She can just watch it go by and decrypt it on the fly. Now, in some ways, having those static keys is actually very convenient. Let's say that you are a bank and you want to maintain a separate audit trail or log of all transactions to your web server, to your e-commerce server. Because if that server is compromised, well, you can no longer trust the logs on it, because a hacker could break in and then modify the logs. So you can actually watch those sessions go by, and you have a couple of options. You can just stream the encrypted sessions to disk, and if you ever need them for forensic purposes, if you need to go back and say, hey, somebody broke in, or oh, a customer had a problem with the connection, you can just that particular session, bring it back off disk, decrypt it on the fly because you have Alice's private key, and read it out. You can also decrypt things while they're happening on the wire, just watching the communication go back and forth. I can decrypt that data, and yet I can send it off to disk, right? So that makes it really easy to do security, to do debugging, to do forensics, things like that. As long as you have a copy of the private key of the server, then you can, without interfering with the connection, without slowing it down at all, you can decrypt the session and then do whatever you want with the clear text. Now, there's some obvious challenges to that as well. Because Eve, they're watching the conversation, is not always your friend. So let's say that Alice is running a bank and Eve somehow gets a copy of Alice's private key. She could literally just sit on a Starbucks network somewhere and look at Wi-Fi sessions, people doing online banking with the Royal Bank of Alice, and she could read their sessions, right? And so she could pull out account information and credit card numbers and whatever else. And that is a big problem. That's a big problem for kind of the security and validity of e-commerce and transactions and things like that. And of course, Eve can get that private key lots of different ways, right? When we just saw this massive breach at Equifax, where we got 140 odd million records compromised because some IT administrator somewhere used admin as a username password. So if that's the way that 140 million accounts are secured, you can be sure that not everyone stores their encryption keys in ultimately secure ways. So Eve could maybe break in to a server and get a copy of the key. She could have a social engineering attack where she poses as some IT person or something and obtains a copy. Or, and this actually is an important reason that's kind of driving a lot of the changes that we'll talk about, she could brute force a connection, right? If you have enough computing resources to throw at an encrypted session, you can eventually, go through enough kind of combinations to keep trying to decrypt that session using different numbers, using different basically keys that you've made up, and eventually you'll get a clear text string out of it, right? So, back in the day where you had to run and maintain your own data center to do that, maybe that was feasible only for kind of government agencies. But now with the kind of easy access to large-scale cloud computing, where you can spin up 1 million servers if you need to for a couple of hours to go break a session, it becomes computationally feasible to go do this. And this is the really big deal. If Eve can decrypt one session where someone is talking to Alice, then she can decrypt them all. She can decrypt all sessions where anyone is talking to Alice. Obviously, that's a big problem, right? That poses serious security problems, because if a bank, if Amazon, if any other online retailer, if the sanctity of their private keys is compromised, then any sessions with that site are susceptible to interception. That's a big problem. So now we're going to introduce a term that you may have seen if you're kind of following along some kind of encryption discussions. There's a term called forward secrecy, right? So we've discussed the problems that Eve can cause if she obtains a private key, and basically without reliable encryption, it's hard to kind of trust doing business. So encryption standards decided that the world really needed some kind of new scheme which didn't use the same keys every single time, and those keys needed to be single use and temporary. And the term of art in this case, the word that is typically applied to these temporary session keys, is ephemeral. And ephemeral just means use it once and then it goes away. So these ephemeral keys are used in a key exchange protocol called Diffie-Hellman ephemeral. So earlier, the first example, we went through Diffie-Hellman key exchange. So basically for Diffie-Hellman ephemeral, that key exchange mechanism is extended to create a temporary one-time session key. And so even if you compromise that session, let's say you brute force it and you figure out the key that was used for that session, you can't use it to decrypt any other communications with Alice. And that's why this is called forward secrecy, or sometimes you'll see it called perfect forward secrecy, because compromising one session doesn't give you access to any future sessions. And I'm not going to go through the math of Diffie-Hellman ephemeral, because that would take a lot more time than we have today. Okay, so quick history of SSL and TLS. As you can see, the internet has been through several revisions of encryption standards, and basically a new version will be released, and after it's out for a while, security researchers and hackers and everyone else do their best to try to find exposures or weaknesses in either the key exchange or some of the actual ciphers, like the things that are used to turn like the plain text into bits using the keys. And whenever weaknesses, enough weaknesses are found, or perhaps people find faster way of doing things, they introduce a new standard. And occasionally, when enough serious weaknesses have been discovered in a particular encryption standard, then it is deprecated. And when it's deprecated, that just means basically it's no longer supported. You're no longer sort of allowed to call communications secure if they're using those really old standards. And that's what's happened to, like I said, as recently as the SSL 3.0 standard, which was deprecated in 2015. The original SSL 1.0 standard was kind of released and sort of immediately deprecated, because immediately upon publication we found lots and lots of weaknesses in it, so that was quickly replaced with the SSL 2.0 standard. And again, just recapping, the terminology SSL and TLS being transport layer security, those are typically used interchangeably, but now if you say SSL, what you're really meaning is TLS, which is just it's a slight expansion of the SSL spec to handle more types of connections. Then there's a new scheme which is currently in draft mode, and that's the TLS 1.3 spec. And that's what we're really talking about here, is the move to TLS 1.3, and ephemeral keys. So the big change here, and by the way, the ephemeral keys, those temporary session keys, the kind of technology that the standards to support that have been around for a while, but they just haven't been largely deployed in practice. But at least the TLS 1.3 draft, which is currently being circulated, only supports the use of key exchanges with ephemeral keys. So if you're using static keys, that's not even part of the TLS 1.3 spec. There are some other changes in TLS 1.3. There's a big performance improvement. So if you are visiting a website that you have visited before, then the initial key exchange setup will happen faster. So that's kind of a nice bonus. And if you look at the, if you, go online and read the spec, you'll see in many ways the TLS 1.3 spec is actually a lot simpler or shorter than, let's say, the 1.2 spec, because TLS 1.3 removes support for a lot of older, less secure, again, key exchange mechanisms and ciphers. They've been shown to be, insecure, unsafe, easily cracked, etc. So they're just removed from the spec. So basically, if you're supporting TLS 1.3, you can no longer use those. So what does this mean for, let's say, IT and security deployments? What does this mean for Eve and you? What it really comes down to is Eve can no longer decrypt, those arbitrary sessions. She can no longer decrypt sessions with Alice, even if she has a copy of Alice's key. Even, in fact, if she has a copy of Alice's keys and Bob's keys, she can't decrypt that session because of the way these temporary or ephemeral keys are set up. And that means if Eve wants to inspect a connection, and Eve can be, good or bad, can be for security purposes, could be a bad guy, whatever, Eve has to actually sit in the middle of that SSL connection. So two terms that are commonly used to describe Eve's sort of role in the network here: man in the middle or an SSL proxy. Often the phrase man in the middle is kind of a pejorative term. It's typically or often used if you're talking about doing this for sort of nefarious purposes, and it's an SSL proxy if it's something that you buy and deploy yourself. Basically, the way it works is that Bob trusts Eve. Bob trusts the encryption keys that are installed on Eve. So when Bob wants to talk to Alice, he explicitly communicates with Alice through Eve. So there's an encrypted connection, the kind of key exchange that we just talked about, although perhaps using ephemeral keys, between Bob and Eve. And then Eve goes and creates a new connection to Alice. Alice responds, and Eve responds back to Bob. So there are these independent sort of pairs of encrypted connections between one endpoint and a proxy, and then between that proxy and the ultimate destination. And then it's the responsibility of the proxy to basically stitch these connections together. And so long as Bob trusts, again, the keys, the certificates and keys that are installed on Eve, this is completely transparent to Bob. Like, if I'm Bob and I'm connecting to Google or Facebook or something through a proxy, through my Eve, my browser bar looks normal. I get the little green key, so it looks like everything is secure. And in fact, everything is encrypted. And that's because the little green lock or whatever you get in your URL browser that shows that the connection is secure, what that really means is it's encrypted, and that the connection, the encryption, has basically been signed by someone you trust. It doesn't actually mean, when you connect to Facebook and you see the little green bar, that doesn't actually prove that you have an encrypted connection directly to Facebook. It just means you have an encrypted connection, and that connection has been sort of signed or verified by someone that you trust. And so that's what you see. So it's largely transparent to Bob. So in terms of practical implications, that whole convenient thing of saying, hey, I'm a bank, I'm an e-commerce site, and anytime someone connects to my web server, I want to be able to just stream that off to disk and encrypt it later, or encrypt it all on the fly, passively, and record the clear text stuff to disk. That no longer works, because if you're using ephemeral keys, as we discussed, you just simply can't passively decrypt those sessions. You have to be a proxy, right? You have to sit in the middle of the connection and actively participate in it. Now, two terms that you'll typically see are forward proxy and reverse proxy. A forward proxy means I have users on my network, and those users are going out to the internet, right? And so maybe I want to make sure that my users aren't downloading malware into my network, or I want to be sure that users aren't maybe leaking sensitive information out, or maybe I'm concerned about some kind of malware infection on my network and it's filming home out to external servers and using encryption in some cases, and I want to inspect that so I can see what's going on. That's a forward proxy, as opposed to a reverse proxy, which you deploy when, let's say, there are users out on the internet, not your employees, but users, and they're connecting into a server that you own. So that the reverse proxy sits between your servers, your e-commerce or whatever, your web servers, and users connect in from the internet. They go through that proxy, and some names that are common in the space, like F5 and A10, that will combine functions like the SSL proxying with things like load balancing across those servers. Now, some security devices, UTMs and firewall devices and such, will have built-in SSL proxy support. So if you're deploying a single firewall or UTM device or something like that, there are some of those which will do the decryption and re-encryption themselves, often at a heavy performance penalty. Like there's a published NSS report that shows you get performance degradation of up to like 85% if you're doing this on your firewall and it doesn't have dedicated crypto hardware. But certainly there are some that that will do this. But the real problem with kind of doing decryption and re-encryption, this proxying on your security devices, occurs when you have more than one inline device. Obviously, a security best practice is to deploy what we call defense in depth, which means you may have a firewall and an IPS, or a firewall and an IPS and a DLP, like a data leak or data loss prevention device. And so you've got, every packet, let's say, has to go through multiple security devices on the way from, a user out to the internet, or vice versa. And if each of those is doing its own encryption and decryption, there are two big problems. One is performance. Obviously, if you have to wait for all this, kind of SSL handshaking between me and my firewall, and then the firewall and the IPS, and then the IPS and the DLP, and then the DLP on the external side, that's going to impose a significant performance penalty, right? And I'll have latency issues for connection setup, I'll have throughput issues, things like that. Also, it causes some challenges for security policy. Let's say that on your firewall and you're dealing with encryption, you want to set a policy that says, hey, users on the inside of my network can't even talk to an external website if it's using weak encryption. Let's say it's using 128-bit keys or something like that. Well, if the firewall is connected directly to the internet, fine, but if it's got to go through an IPS and some other device, it may not have real visibility into the kind of encryption that's used out on the internet. So that means you can't write security policy relevant to encryption on that device. So those are two of the big challenges with trying to do encryption on individual security devices when you have more than one. So it's much more efficient from a performance perspective, and also better from a policy perspective to deploy a single decryption device that can basically do decrypt once, inspect many. So something that can offload the encryption from all those security devices, let them all do their thing, and then re-encrypt the data and send it on its way. Sometimes you'll see this done in like a dedicated kind of standalone SSL appliance, or you can do what we've done, which is build this active SSL capability, the SSL proxy capability, into a network packet broker. So this is a pretty big deal for us. We here at Ixia, and we announced this, I guess, at Black Hat. Next quarter, in October, we'll be releasing our active SSL capability on our industry-leading Vision 1 packet broker. And one of the great things here is you can use that encryption decryption capability that we're now adding with all the other great features we have for supporting security deployments already built into our network packet brokers. For instance, on top of the 10 gig of SSL capability that we're giving you, and with this dedicated cryptographic processor, which is important because since it's dedicated, it's not consuming other system resources, right? Doing encryption on our packet broker isn't going to slow down anything else that it does. If you're doing NetFlow generation, you might be doing something like data masking, where maybe you're monitoring e-commerce connections, and whenever you see a credit card number, yeah, you want to send that off to a recording device, but you want to overwrite all but the last 4 digits of that credit card number just for, you know, compliance and security reasons. Yeah, you can do that, and doing encryption doesn't slow down your ability to do that, that data masking. Now, when you're doing a security deployment, there are two kind of major categories of security tools: inline tools and out-of-band tools. Inline tools are things like firewalls and typically IPS devices, intrusion prevention systems, which means a packet has to flow through that device on its way from, say, client to server. And then that security device, if it sees something it doesn't like, can just stop that packet, cannot forward it. Passive or out-of-band devices are typically things like network capture or recording devices. A lot of times in IDS, intrusion detection systems, are deployed out of band. So it's very important to be able to support both types of security products in, in a security deployment, and that's obviously something that we can do. Another important question that will kind of come up when you're deploying SSL is, especially if it's the case where you have users and they're going out to the internet and you want to make sure that like they're not downloading malware or something like that, you may want to bypass inspection for certain categories of websites. Maybe just for privacy issues, you want to say, hey, don't inspect healthcare traffic or don't inspect banking traffic for my employees, just because you're concerned about sort of a breach of privacy, right? So you say inspect everything else, run it through my malware engine, my whatever. But if it's those sites, then leave the connections encrypted. Now, if any of you are familiar with Ixia or previous Anui packet brokers, you know that ease of use, kind of a really easy to use UI, is one of our real hallmarks, and we continue that certainly with our SSL appliance. So a typical deployment for a security deployment, well, it's sort of something like this, where you'll have multiple security tools, again, firewall, IPS, data leak prevention, maybe a threat intelligence gateway, all plugged in. And one of the reasons that it's really nice to have this SSL capability built into something like a packet broker, especially one with really good support for security deployments, is the ability to kind of flexibly support and route traffic. Let's say that you have a 3 gig internet pipe and your IPS, your intrusion prevention systems, can only run at 1 gig each. Well, you might need the ability then to load balance traffic across all of those. And if one of them fails, you want to be able to take that device out of the rotation. And let's say you upgrade your pipe to 4 gig. You don't want to do a forklift upgrade where you throw away all of your IPS systems. You want to be able to just add one more and add it to the load balancing rotation. Ixia has been doing this for a long time, so we've got really good support for that kind of load balancing, including heartbeat support. And a heartbeat packet is basically a specially crafted packet, and we have different packets for different kinds of security devices. And we frequently send these through all the attached security devices. And if that packet doesn't make it through, then we know, hey, that device has failed. So automatically take it out of the rotation. So maybe you're just taking something down for administrative maintenance. You won't need to do a system upgrade. Yeah, we'll detect that automatically, and we'll stop sending traffic to it, and then we'll notice when it comes back up. There's a lot of other kind of features built in or optional on the Vision One platform. Maybe after you decrypt traffic, you want to generate NetFlow to see what's going on, and we offer very rich NetFlow with things like application identification and geolocation and like custom application support. You can tell what kind of handset, what kind of browser someone's using. So it's very nice to be able to do that kind of thing in conjunction with, with your decryption. The data masking I've already talked about. So this is a really nice combination of features. And if you think, well, basically SSL is kind of a feature now that you can add on to a device, a packet broker with great security support is an ideal place to put that. Now, one of the things that we want to make sure happens is when you do, an SSL deployment, obviously that could break things, right? And so our design goal was to make sure everything sort of works right out of the box. You drop this on the network, and connections flow through, and we preserve whatever encryption would have happened otherwise, and we make it really, really easy to get up and running. And then if you want to apply more granular or specific policies, say you want to pick which external root certificate authorities to trust or not, or you want to add your own, you can easily go in and do that, but it's not mandatory. You can get up and running without that kind of customization. And then as you go on, you want to clamp down your security policies or maybe apply different kinds of policies for different groups of users or things like that. It's pretty easy to just point and click your way around the UI and do that. Okay, so wrapping up, on the upside, the internet is about to get a lot safer, and in fact, encryption, will be both safer and a little faster with a TLS 1.3 spec. But if you're doing security deployments, in many cases, life is about to get a little more difficult because some of those passive SSL things that you've deployed in the past are simply not going to work anymore. And that means a lot of systems that people have deployed for monitoring access to their websites and things like that are going to break, and that's kind of a negative. And by the way, this is a kind of a big deal because certainly well over 70% of internet traffic is encrypted today, and so, and that includes malware transmission, right? I mean, if I'm a bad guy and I'm trying to push malware into your network, well, of course, I want to make sure that that download, that transmission of malware is encrypted, because that makes it harder for your security devices to stop the transmission of that malware, right? So already more than half of malware downloads into networks are encrypted, and you can be sure that that number is only going to increase quickly, right? And that's why it's really important to figure out how you want to deal with encryption in your environment, whether it's the inbound use case, that reverse proxy use case where things are coming in from the internet and talking to your servers, or it's the outbound use case where your users are going out to the internet and you want to make sure that you can inspect what they're doing or what they're downloading. It's going to be pretty important to figure out how you want to deal with that in your environment, because encryption creates a blind spot from a security perspective, and also performance monitoring and troubleshooting, and bad things happen in blind spots, and so you want to engineer your way out of having those kind of blind spots in your network. Ixia can be a really good partner in helping you get better insight and more control over your traffic while driving your cost of deployment down, and that's a really good thing. If you would like to do some more background reading on this, I've included a couple of links here, and obviously you'll have access to the recording if you'd like to reference these later. Wikipedia, of course, is always a great reference, and I shamelessly cribbed some example data from this Wikibooks example. And again, if you want to do more in-depth, detailed reading on kind of how Diffie-Hellman key exchanges work and things like that, it's a pretty good reference point. Okay, and with that, we have some time for questions. So, Alexandra, I will pass the ball back to you to see if we have received any.
Yes, we have received quite a few. So I'll just start going through the list, and hopefully we can get through as many as possible. Okay. Does TLS 1.0 have a tentative scheduled end of life?
So it has certainly not been announced. I mean, if you think back to that slide, typically standards stick around for a while. I think it will probably be some time before it is deprecated. I mean, even though the TLS 1.3 spec won't support static keys, and frankly, I expect the adoption of TLS 1.3 to be fairly rapid, mainly because a lot of the companies who have kind of a vested interest in stronger encryption, and I'm thinking, Google, Microsoft, Apple, just to pick a few, they own both ends of a lot of connections, right? They own the servers and they own the browsers, right? So they own the client side. Browsers are all auto-updating now. You don't ever have to go in and update your browser manually. It just happens, right? So I expect adoption of TLS 1.3 to happen really quickly, whether people kind of plan for it or not. But So that means I expect its use to be very widespread, but that does not necessarily imply that TLS 1.0 will be deprecated soon, if that helps.
Awesome. Man in the middle or SSL proxy also means that it will be useless to use a tap to duplicate traffic for analysis purposes.
Mm-hmm. Yep. Yeah, if you want to be able to inspect encrypted traffic, you certainly, like today, if traffic is encrypted, if you just have a tap, yeah, you're not going to do anything with it. But if you have a passive SSL decryption device, and honestly, that is also built into our Vision One packet broker, you can hook a tap up to the packet broker. We can do passive SSL decryption and just watch those connections on the fly, and then stream clear text data out. But absolutely, one of the big changes that people will need to plan for is if they want to inspect in traffic which is encrypted with TLS 1.3 and the ephemeral keys, you will absolutely need an SSL proxy in order to inspect that traffic. So yes, that is absolutely correct.
Awesome. If Eve cannot decrypt sessions, even if she has Alice and Bob's private key, is there still value in having individual private keys?
Well, so again, the server keys are important. The client keys are typically not so important. But there's value beyond just encryption in keys and certificates, and part of that is knowing who you are talking to, right? I mean, if a certificate is signed by someone you trust, there is value in knowing sort of who you're talking to. So there is encryption, even though we use the word encryption a lot, there are a lot of other kind of features that go along with that, like non-repudiation. And so, yes, there is value in people having unique keys. And the key exchange that we went through still, like even when you move to ephemeral keys, you're still using that initial key exchange that we went through for the initial connection setup, and that relies on a secret private key and then a published public key. Without that, the whole thing falls apart. So yes, there is definitely still value, and in fact, a hard requirement to have those.
Awesome. Can you comment on SuperStack compatibility? Because I have a backbone with Cisco equipment.
I would probably have to take that offline, and honestly, I'm assuming that SuperStack is like an Ethernet encapsulation technique. If not, feel free to contact me on Twitter or my email here. So typically you can, I mean, if it's an encapsulation technique, you can typically do all the stuff that we've gone through and either remove or preserve those headers. You might strip them off before you do your decryption and then reapply those headers on the way out. Although certainly there are things like encapsulation and networking techniques that can make it harder to do, in part because when you're doing man in the middle, you certainly have to have access to every packet. If you miss a packet, the whole thing falls apart. So your networking scheme has to support kind of funneling all the traffic in a session through a single point, if that helps.
Awesome. I think so. I haven't received anything back yet.
Yeah, feel free to contact me directly, and I can do some more research to dig it up.
Yes, I sent him your email directly since his question was even longer than what I read off to you.
Okay, thanks.
How is active SSL related to open source libraries such as OpenSSL?
So let's see, how is it related? So typically an open source library will, like OpenSSL, certainly will support whatever the latest encryption standards are. I mean, when TLS 1.3 is ratified, you can certainly expect OpenSSL, kind of right away to support TLS 1.3. Now, how are they related? I would say that often the endpoints, or at least the server side of a connection, will use that open source library like OpenSSL as its TLS 1.3 implementation. You could certainly leverage open source libraries like OpenSSL if you were building a man in the middle or an SSL proxy, although there is a lot more to it than just the encryption decryption, right? If you're building a proxy, you have to be able to do things like sort of transparent layer 2 through 4 intercept and maintain state and connection tables so that you can correlate a connection on one side of a proxy to a connection on the other side. But certainly you could use that as to help you just with those key exchange or the initial encryption setup. Remember, when you're using an SSL proxy, there are multiple encrypted connections, one between the client and the proxy, and one between the proxy and the external server. So certainly you could leverage something like OpenSSL when you're building your SSL proxy just to help you establish those encrypted connections. But there's a lot more to it than just the encryption piece.
Great. We have time for one more, so I'm going to combine two questions. I feel that they are similar. The answer will be similar. So,
okay.
What is Ixia's competition in the area of SSL decryption, and could you also explain the differences between Ixia and Gigamon?
Okay, so competition in the space. So I mentioned now we're not really focusing on the reverse proxy space. I mean, certainly, you could use us in certain applications for that inbound space where, let's say, F5 and A10 are really kind of the dominant players. But we're not trying. We don't do like server load balancing and things like that. So specific deployments it would make sense, but not in like kind of large, multi-server deployments if you're looking for all that load balancing capability and things like that. In the outbound space, there's certainly SSL proxies, kind of dedicated appliances that we would compete with. There's Bluecoat, Cisco, OEM, Swan. I mean, there's a couple other out there. I know some of the other players like that, A10, F5 have been in the space, but no one else really combines. None of those combine the kind of SSL capability and then all of the packet broker capability that we talked about in one chassis. And the reality is SSL is a standard, right? I mean, my SSL and your SSL, if we both follow the standard, are going to look a whole lot alike, right? I mean, there may be differences in like performance and maybe UI usability, but the core SSL piece is really going to be the same. And that means the differentiation between kind of using a dedicated, let's say, SSL appliance and using something built into a packet broker is largely going to come down to how well it does all the other stuff, like how well does it support your security deployment? Can it do load balancing? Does it have heartbeat support? Can it do the netflow generation? Can it do data masking? Can it do all the other things like that? And so really, if you're kind of thinking about building this into a packet broker versus often having a packet broker plus one of those dedicated external devices, a lot of the difference is really going to come down to that. Now, us versus Gigmon, I mean, I could go on for a long time about that. One of the big differences here is performance. We've got a 1U system that can do up to 10 gig of SSL, and last I heard, even a 2U fully decked out appliance from them could only do about 6 gig in total. And if you're doing that level of SSL, you can't do any of the other advanced features like data masking or netflow generation or things like that. So we've got much better density, nearly double the performance, and a lot of the other capabilities like what's included in the netflow generation. Can you do geolocation? Can you identify what browser is in use and things like that? Simply aren't available on that platform. Again, I mean, I'm not I'm not really here to sort of competition bash, but feel free to contact me directly, and we can go into more discussion about kind of what you're looking for and what might be important on your network and what the differences are.
Great. Thank you so much, Scott, and thank you to everybody on the line who joined us today. You should receive an email from me later today if you are a winner of the hoodie. I also pasted the names of those who won in the chat window. And as a reminder, we will be sending the presentation slides in the on-demand replay shortly. If you have any questions, feel free to reach out to me, acassandro@ixiacom.com, or Scott. He gave his email at the beginning of the presentation, and I believe it's showing on the screen now. And we will be happy to answer any of those questions that were unanswered. And thanks again to all who joined us today, and we look forward to seeing you on a webinar in the future. Thank you.
Thanks, everyone. Great questions. Bye.